Okay, so we have some entertainment tonight. This should prove interesting.
Why don't you call it, instead of entertainment, call it program?
Program.
Education.
Well, if I say education, it's liable to scare some people off. If I say entertainment,
Get educated.
they're liable, more people might show up. But this has to do with telemetry, and probably telemetry at the cutting edge of things. But I'll let Randy tell you about it, since he got nominated by Kyle to do the introductions tonight.
Well, a couple of months ago, about 3 or 4 months ago, I was at Dartmouth, and we were flying there, and Bob McGowan was there, and he was doing some testing of his Icon aircraft, and he brought a new friend along, and his friend had set up a telemetry system on board his aircraft, and his friend's name is Francesco. I forgot your last name. But he's here tonight, and he would like to do a presentation for all of you on Sailplane telemetry and being able to do data collection and analysis of the different phases of flight, both launch, ascent, cruise, descent, maneuvers, and landing. But I believe for tonight, he's going to focus more on launch, which is what Bob was undertaking with Francesco's telemetry system. Go ahead.
Get my big head out of the way here.
That's a little bit high.
Thank you very much for inviting me. Like you, I fly gliders since the year 2000. Initially, I've been slope soaring. Then I took on F3J in 2006. I've been team manager for the F3J Italian team in 2007, 8, and 11. And in between, I also been a pilot for the Italian team in the European Championship. And since last year, I tried to, with some recent success, with F5J, the EU electric class. FAI is currently regulated. But I mostly fly F3J, and probably recognize in this picture one of the typical man-on-man launches with monoline in F3J. Yeah, because F3J is a man-on-man competition with a minimum of 6 pilots flying together, and I've personally seen as many as 15 in the same flight group. We don't use winches, but we use 2-man tow with 500 feet of monoline, which is capable of storing an incredible amount of energy, as Bob probably knows even better than I. F3J in F3J launch has an enormous importance, probably way too much than would be comfortable. And there are a few basic tenets in F3J launch. If you don't launch high enough, you lose your round. Well, not always, of course. If you don't launch fast enough, you have a good chance of losing your round, because it's easy enough. You can find someone who has launched faster than you, and the time spent on tow doesn't count towards your score. And most important, since you have 2 people towing for you, if you don't launch strong enough, you lose your friends, because they will not be happy to tow for you, because you make them run too much. So launch is a phase that you definitely want to optimize. And this is a snippet that I took from a message that Giovanni Galizia, who would then become the junior world champion in 2008, sent us after the F3J Euro Tour France contest. Basically, he said that they had been watching the German guys, and the German planes launched very fast and very strong, much faster and stronger than the Italian planes. So we need to understand why and quick. And of course, quick was because only 1 month was left before the championship. And well, of course, at the time we didn't understand very much, because even in principle, there are only three things that come into play when optimizing the launch in F3J, which is the launch camber, the launch elevator preset, and the tow hook position. So only three variables. It cannot be that hard. Unfortunately, it turns out it is, because most people don't set a goal, don't set a clear goal when trying to optimize. And they don't have any way to measure their outcome and compare the outcome to the actual goal. And even if they do, one of the problems is how to analyze how the different parameters influence the outcome. And if you don't do anything in this regard, it's very hard for you to find a path to improvement. Optimization, the ultimate goal is to extract the maximum energy in the shortest time, which is like saying the maximum power. Well, time is very easy to measure because we all have stopwatches, and it's a non-issue. But how to measure energy? Energy at the end of the launch comes in two basic forms: in gravitational potential energy, that is how high the model is, and kinetic energy, that is how fast the model is flying. So we need to find some way to measure altitude and speed, or better said, airspeed. And there are a number of tools to do so on the market. These are just three of them: the Eagle Tree telemetry system, top left, the Unilog telemetry data recorder, top right, and one of the altimeters / limiters that we use for F5J or ALES. When you actually use one of those and you manage to successfully log a launch, you end up seeing something like this. It is a very simple graph showing altitude over time and airspeed over time. Well, altitude is more or less what we expect. The plane is climbing, and then you have some zoom. You see the dive and the zoom. But what about airspeed? This pattern is characteristic in F3J, and it's kind of strange. Why is the airspeed increasing very fast and then settling down to a lower level and then increasing again, but much slower rate, and then increasing again? So this is exactly what we need to understand. But in order to obtain such a good data sample, you have to be a little bit careful about how you install your system. So this is the poor man's approach. You wrap your data recorder in any suitable plastic, in this case some heat shrink steel, and you just stuff it in your fuselage. Well, if you're lucky, you can find room for that. But as soon as you no longer want just an altimeter, but you want to measure airspeed, and you have a pitot tube, well, things start to become really complicated. You definitely don't have enough room for everything. So the way we approached this issue was by designing a shell to host all the data logging and the transducer equipment inside a self-contained system which can be installed on top of the wing. So it was designed by computer design, and then we CNC milled a plug, we made a mold out of the plug, and we started pulling out parts such as this, which can be installed on basically any F3J airplane, because thickness and cord and cameras are not that different from one plane to another. So it works pretty well with the Explorer, with the Pike Perfect, the Supra, the Maxa, and the Icon.
Francesco?
Yeah.
Is that the static on the side?
On the side, no, it's a switch.
Oh, okay.
The static is actually in the back. You will see it in the specimen, because one of the benefits of having that we decided the shape of this shell is that we were able to compute where exactly CP is equal to 0 for the static port. And this is what's inside. Inside the shell you find the data logger itself, the airspeed, the transducer, a battery, so that you don't need an external battery. Everything is self-contained. switch and the transceiver for telemetry that we talked about that in a few minutes. So once you have this information, and you have altitude and airspeed, you pretty much find that this is just enough for understanding the end state of your launch. It doesn't tell you much about what happens in the 2 to 5 seconds, which are an F3J launch. So we need something more if we want to understand what's going on, if we want to understand why that particular shape in the airspeed graph. And in particular, we want to understand how does energy flow from the towing system to the plane. Because we all know that towmen pull the line and the line pulls the plane. So the line must be an important factor in this equation. And actually it is, because it's the main medium for energy transfer, especially because we use monolines in F3J. The line stretches quite a bit, let's say at least 40% at the braking strike. Of course, we don't arrive up to the breaking point, but it's safe to assume that any line stretches up to 20 to 25%. So it's essentially a spring.
Are you restricted to a specific size of or type of line?
It has to be a monoline and has to be made of nylon.
That's it.
Yeah, that's it. Then it's up to you, size, and of course the length is limited.
Right.
So we need to find out a way to measure line tension if we want to understand something about energy transfer. Well, it turns out that a suitable load cell was already manufactured by a French modeler at this website, and it's a very simple device that attaches to the tow line and it hooks onto the tow hook, and has an electrical cable that brings the analog signal to the data logger, and it has a particular connector so that it can disconnect safely upon release. So you can actually record the line tension during launch, during these 5 seconds. And when you do that, you end up with a graph like this, in which you have airspeed, altitude, and traction. Oh, I need to apologize. All these graphs are metric units. So you have altitude in meters, airspeed is meters per second, and traction is newtons in this case. And so you see something interesting. Something interesting is that airspeed and traction look alike, but with some phase inversion. And things get more and more interesting when you try to relate the shape of this graph and the features of this graph with the actual trajectory that the model follows. So I'm sorry, this is very hard to see in this picture, but the lower right is a composite picture taken by assembling individual frames of a video in a single frame. So you can actually see the path that the model follows. And so it's easy to find out that the initial peak in airspeed is precisely the moment in which the plane starts to fly. I mean, when the plane is released, it's not flying yet. It's just pulled towards the turnaround by the strong tension of the line, so it quickly accelerates and rotates, and at a certain moment, the wings have there isn't enough airspeed for the wing to produce lift. And when the lift starts to counteract the pull of the line, so it gives up airspeed in order to increase tension again, and then in tension and airspeed seem to play with each other, and they are both increasing up to the point in which the pilot starts to dive, and in this case there is a very sharp acceleration to the expense of tension, and then the model releases from the tow line, the connector separates, and the recording for tension finishes. Since these are all numerical data, you can actually start to analyze or reduce the data that you collect in such a way that you understand what are the forces that are coming into play. So these two figures depict the situation at the beginning of the launch, when the model has just left my hand, and when the model is already rotated, and the forces are actually the aerodynamic reaction and the traction are counteracting each other. It is no longer traction dominated. And if you want to go to follow this route, you can do any kind of interesting analysis, such as this one is an energy analysis, and you can actually calculate the three forms of energy: elastic energy, gravitational energy, and kinetic energy, and add them up, and you find that there is some energy which is missing, and the energy that is missing is actually the energy that is wasted against the drag forces. And if you do the math, you come to an interesting conclusion, which is that in an F3J launch, the line is responsible for half the total drag. That is, the line has basically the same aerodynamic drag as the airframe itself, which is very interesting and brings us some interesting conclusions. Is that you definitely want to have the thinner line, the thinnest line that you can afford, in terms that doesn't break under your tension. For example, a big plane like Bob's Icon, I think needs a thicker line than a smaller plane like a Supra. Other interesting conclusions, again, I'm sorry, it's not very clear, is that if you analyze the climate path, you find that it typically shows at least two humps which are related to this particular point, this ringing, I call it, between the tension and airspeed in the log graph. This pumping is actually an energy transfer from the line to airspeed and back. And since every energy transfer is never 100% efficient, we definitely want to eliminate this. Ideally, we would like to have no hump. Well, no hump requires a very good launch technique, and probably the only person in the world maybe there are a couple of persons. One of them is probably Daryl, and another one being Joe Wirtz. But the second hump we can do something about. And actually, something that we found is that if you move your tow hook aft, that's about between the previous slide and this slide, I moved the tow hook aft by about 1/4 inch, and there is no second hump, and there is no more ringing, almost no more ringing, and final altitude is higher actually. So this is very interesting because moving just 5 millimeters is not that much. And it doesn't take a lot of effort. It's not unsafe because of course the plane has to be retrimmed for this new tow hook position. Some other optimization that you can do, Bob will probably recognize this, is optimization of the zoom phase. So this is a log from Bob's Icon 2. And it was the very first log of the day. Bob's model was unhooking at 50 meters per second, which is basically 110 miles per hour. But with all this energy, was only able to gain 55 meters in altitude. So in terms of energy, the yield of this transfer is only 43%. So something that we tried was to change the radio program and increase the amount of so-called snap flap, which is basically the elevator to camber mix. And by doing so, with the same airspeed, we managed to get 90 meter altitude gain. So with the yield moved from 42% to 70%. And
What was that change again? did you change for this?
Oh, we just changed the radio program, and we increased the amount of snap flap.
So elevator camber mix.
Yeah,
Instead of camber only?
sorry?
Instead of elevator camber, it's just camber
Oh, you need to,
previously?
yeah, you need to think that this is, at the end of the dive,
Okay,
camber is already reflex.
right.
So at that point, you want your model to be able to develop the highest possible coefficient of lift.
Okay,
And to do so, you increase your camber.
okay.
And it was simply not enough. So I remember Bob was quite happy at this point.
Yeah, I think,
So you increase the camber just at the end of your toe,
Exactly.
and what it does is it stretches the line more, so you get more.
No, he's actually talking about the zoom phase.
Yeah.
So you
So
got
you're
max
off-
tension like you're talking
Then you're
about.
off the line.
And then we dive
Right.
to exchange the line tension for speed.
Speed, correct.
And then we got to do a sharp pull out. The sharp pull out is what we're talking about.
That's what you add to the camber.
Traditionally in the United States, we just use up elevator and the camber doesn't change at all. Maybe it stays in reflex.
Oh,
And,
I see. But you need to lift, you need to lift on the wing.
Ideally, you want
To rotate.
the lift to rotate it up.
Okay.
And I had been experimenting with a little bit. I had mine maybe going down, I don't know, 3/16 of an inch or something. And then, but we probably tripled that amount. Probably goes down
Yeah, as soon as-
3/8 or half inch almost.
But as soon as you finish the reflex, you go back into, as soon as you finish with that part, then you go back into full reflex.
That's
To
right.
penetrate as well as you can.
That's right, to zoom on up to the altitude. As soon as you release that up elevator stick, automatically the flaps and ailerons will go back to reflex.
So you actually changed the camber of the wing from your toe? You have more camber or less camber than you when you were in tow?
The full up elevator is roughly equal to the max amount of camber we use for the climb up portion.
The reason being
So you have it mixed without, you have it mixed, the camera mixed with elevator.
Yes, in
Yeah,
the
camber's
reflex
link.
mode. So
Yeah.
just as you're pushing over to start your dive, you flip out of launch mode into reflex mode. But that reflex mode's got that snap flap programmed in with the full up elevator.
Gotcha, okay.
So when you're diving, it's in reflex. It only goes to that large amount of camber when you pull up for a split second.
Okay.
Yeah, you could do it manually, but it's better if it's automatic because it's too quick.
this is all applicable to winch launch as well, right?
No, absolutely.
Yeah.
Absolutely.
Yeah.
That's really interesting.
That's how I keep losing.
Amazing.
Yeah,
So-
I don't think anyone except in the States uses as much snap flaps as Francesco and now I use.
Is that a launch only setting and then you reduce your snap flap for normal flight, cruise mode?
Well, it's only coupled in, that snap flap amount is only active in reflex mode.
Okay.
So maybe what you're asking is when I'm in reflex mode penetrating home from downwind, is that snap flap program in there? Yeah, it is, but I'm not pulling full up elevator
Okay.
Yeah.
when I'm flying around like that, so it doesn't
So
matter.
you have a max camber in reflex mode, which is different than the max camber in cruise mode
Cruise
or thermal mode.
Yes,
Okay.
yes.
Good, that's right.
But if you have a flight phases to spare, you could have a separate phase
For launch.
just for zoom.
You could do that in launch mode, yeah.
So, so all this is very interesting, but it's actually not telemetry. This is just data collection. But of course, data collection comes first because you have to have some data if you want to transmit back to Earth. So real-time telemetry is actually a useful addition, and potentially it's another game changer. It's right now it's not allowed by FAA rules except for safety reasons. For instance, you can actually, it is allowed to relay back to Earth I think the radio battery voltage and the signal strength. Nothing else. But of course, this is just the present situation. Things are bound to change in the future. something which is very good right now, it's very good for training. Of course, the pilot should not be looking at the display, so probably it's better to have a telemetry system with audio feedback, or to have a buddy relay relevant information to you and filter out what's not relevant. Especially, it's great for team training. If you have a team that needs to go to the World Championship or just to major contest, this is a very good way to train together. And the telemetry, the data logging system that I personally use, which is Unilog, has built-in telemetry, but it only supports German or European-related systems, such as Broker, Multiplex, and Jetty. And of course, I fly for TAPA, so I'm out of luck. I needed to invent something myself, even, or better said, I had to implement an idea that was already invented, and the inventor was Wolfgang Korsek from the Zurich Polytechnic. It's a 2.4 gigahertz Bluetooth protocol radio link from Unilog to Unidisplay. Unidisplay is an accessory to Unilog. It is basically, the name says it's a display which shows all the information which the logger is currently recording. So these are a few pictures from different stages of my implementation. Top left is the Bluetooth radio module being programmed. Top right, I already have a Unilog and a Unidisplay talking to each other without the serial cable that they deliver with the system, but using a radio link with two Bluetooth modules. Then I have the Bluetooth module installed in my fiberglass shell and a handheld unit to receive the telemetry data in real time. We built this project as a team project for the Italian team in 2011. We built 3 complete units and we used them in team training sessions, many of them. We received data directly into PC, and depending on the situation, we did real-time analysis or deferred analysis. Real-time is very good, especially for things such as finding the best floating setting or finding the best penetration setting, whereas deferred analysis is very good for quick phases such as the launch, so it's very good for launch setup. This is an example how you do, how you find the minimum sync setup with telemetry. So you go to your favorite field very early in the morning, you launch your plane, and you have a buddy reading your sync rate for you. And then if you feel your sync rate is too steep, you can try to pull up a little bit on your elevator trim, and then maybe you find that actually it's not really improving because the plane is now too slow. Then you ease back on the trim until you find the sweet spot. In this case, it was 25 centimeters per second sync rate, and you just call it a day and save your memory into an SD card and not touch. But there are further possibilities, of course. There are interesting sensors already available for angle of attack and side slip, which is basically an angular position sensor. There are sensors for current draw measurement for servos or receivers, or if you fly electric, for your power system. You can measure current, voltage, you can measure RPM, and if your propeller manufacturer gives you figures for how much power is absorbed at a given RPM, software is available that calculates efficiency for you, so that you can optimize the climb performance, or in terms of how many meters per second per kilowatt, or how many meter of altitude gain per milliamp hour. So it's up to you, whatever. Many different possibilities are available. And in the future, maybe we will also have live onboard video feed, which is of course an FPV, like as you were talking earlier.
Future, Dick Rohr did that years ago.
Yeah.
So this is an example of a servo current, or maybe radio gear current draw during launch. You can compare current draw with altitude, and you see, for instance, that in all the initial launch phase, current draw is less than 1 amp. But as soon as you pull up on your elevator for the zoom, and you have all your trailing edge going down and the elevator going up, current has a very marked spike, and almost 2 amps. It's very short, but if the battery is not up to the task, this may black out your receiver. So it's potentially something that it's better to be aware of this. This is another log from an electric motor sailplane. So when I switch on the motor, you see voltage going down, current picking up to almost it's about 12 amps, and altitude, of course, as the model starts climbing. And if you have an RPM sensor, the same software can calculate efficiency for you, which is kind of interesting, of course. And if you have a video feed, and in this case not real time, you can also have some interesting observations, such as this is the tail of the Supra during launch. It's impressive to see how much the tail flexes and twists. Have a look. Oh, sorry. Wrong.
Oh.
And if you have especially with a new model, this may help you in figuring out if you are pulling too much for the table. Another very interesting application of video is to use a yaw string to evaluate how good your aileron to rudder mix is.
I should do that.
It would be interesting if we could have this relayed in real time to the pilot or to a helper.
It's already been done.
Yeah, I guess so.
Yeah.
But the problem with sailplanes, you don't have much room for equipment. So to wrap up, whatever you feel like real time or deferred analysis, everything that you do in the measurement field, sooner or later comes to your advantage. So everything is good in this regard. Very important is to measure and collect the data over time, so over a significant amount of time, because it's the only way that you can compare your performance over time, understand what's going on, and improve eventually. If you have a team that can share the common program for training, this is very important, and the telemetry is a real bonus. Keep in mind that new radios are arriving with telemetry. Telemetry will be integrated. Telemetry data will be displayed on the radio screen, or even more interesting, will be available as a sound output or even speech synthesis. So you can have a readout of your altitude or airspeed or current or voltage, or you can have variometer tones, or you can have alarms for temperature, for maximum current, etc. And the bottom line is that this should allow us to fly more safely. And if you fly a competition, you should allow for better results in your contests. Thank you. Now, if you have any interest, I have here telemetry system. This is the load cell, tension transducer.
Oh, cool.
Yeah. This is connected to the, this is a very simple connector. When the model pulls out, it simply disconnects without breaking anything. And this is the handheld unit. I switch this off. Okay. 15 seconds startup time, sorry. Okay, it's working. So you can actually read the altitude while I'm...
Not without glasses.
The altitude is slightly drifting because there is a voltage regulator that gets hot over time, and the sensor picks this up.
So what's the altitude sensor on that? Is it gyro or?
No, it's a barometric sensor. Yeah.
Oh, it is.
Also, the airspeed is a barometric sensor. Well, of course, I have no specific interest in that, but also GPS data is available with the same system, because it's the same manufacturer also manufactures a GPS sensor, and the same information carrier, this serial radio link, can be used to transfer serial GPS data. No problem.
Is GPS or sensor the most accurate?
Sensor.
In terms of altitude?
Yeah, and speed and everything else.
Oh,
It seems
so-
like the GPS would have trouble determining
Yeah, GPS
how
is...
fast you're going, like vertically.
In vertical resolution, I think in terms of sensitivity, this is higher because it's 10 centimeters sensitivity. But I don't know about precision over time. In terms of speed, of course, if you fly gliders, it's airspeed that is of interest to you, not ground speed.
And that's what you're gonna get with GPS.
Yeah,
You're going to
exactly.
need ground speed and GPS.
Since right now you're going pretty fast. Oh, jeez.
Doing real fast.
There's a fast crowd.
It says you're going 36 kph right now.
What is the maximum tension you are seeing on the line?
Oh, so far the maximum that I ever recorded was 75 kilos. So it's
Wow.
150 pounds.
Yeah.
Wow.
So you know how to preload your line then?
Yeah,
No, it was not
my
pre-
channel
it
lady
wasn't
wouldn't
you.
take that.
You preload your...
Oh, preloading is about 40 kilos. And I know that, for instance, Joe Woods uses to evaluate tension for pre-launch, and he's not satisfied until he reaches 50 kilos.
So based on the tension, you can actually figure out the G loading on the airframe,
Yeah,
right?
this is something that I would love to add, which is basically a 3-axis accelerometer, which you could use exactly for this purpose. But yeah, you can. The sampling rate of the system is about 16 hertz, and it's just enough to be able to calculate acceleration for the very initial split second, maybe 4 or 5 samples. And well, it depends on the weight of your airframe, but I logged as high as 12 Gs.
Okay. So at 25 meters per second, what would be your L over D?
With 25 meters per second, without with a Maxa, which is the model that I currently fly, without ballast is not very good.
Yeah.
It's about 20.
21.
Yeah. You definitely need ballast if you want to fly at 25 meters per second.
What's the best L over D log in dead air? What's a good number?
Oh, 25, 26. And in terms of sync rate, with this new generation of lighter planes, I personally seen logs with 22 to 23 centimeters per second, which is quite impressive.
Have you ever seen logs on free flight stuff?
No, that would be interesting.
Mm-hmm.
It's a little bit heavy for F1 models, but
Mm-hmm.
I think it would be just enough to redesign the shell,
Mm-hmm.
because the shell itself is. I built it to last. I didn't build it
Mm-hmm.
to be light.
On that subject, how much does that whole shell and unit weigh?
Oh, it's 2 ounces.
2 ounces.
Yeah.
And how much did all the electronics, the receiver, how much did that cost?
Oh, it's about $400.
All total?
Yeah.
Not bad.
No, that's not too bad.
How much tweaking was required to,
That's a problem.
Off the shelf.
Because for instance, the telemetry part is definitely not on the shelf. For the shell, we have now we have the mold, so it's not be a problem. And the load cell is it's a little bit expensive itself because it's $150 alone.
Wow.
Yeah. Load cells are not cheap.
It must be
Yeah.
sturdy too, because the parachute's down.
Exactly. Well, there's a parachute to slow it down.
Right.
If you're lucky, you might find one in a place like Halton, where they have electronic surplus. If you can find it, pick it up. Most people won't know
Yeah.
what it is. So, what did you use to calibrate your system to know that you were getting real results?
Okay. So calibrate the load cell is not that hard. I
Right.
just used a number of weights, calibrated weights. And in order to, for the altitude part, I built a small vacuum chamber that I could measure the vacuum, so to see how much, what was the correlation coefficient from absolute pressure to altitude. The tricky part was the airspeed transducer, of course. And so far the best way that I have found was to compare with the reading of a GPS on a closed circuit, so that I could average the wind speed over one pass of one loop in the circuit. It's not very satisfactory, of course, but again, it's if I manage to have a 10% accuracy, I would be pretty happy. I don't need much more for the kind of data analysis that we are interested in.
Yeah, the main thing there is you got data that you can make an assumption from and tweak it one way or the other, and then you can see improvement. That's the whole
Yeah,
goal.
it's comparative, so.
Yeah.
So this is why it's important, for instance, to have multiple sources of data and correlations, just comparing what you see in terms of altitude and the speed with I call it the strobo picture. By assembling individual frames spaced 0.1 second from one another, you can actually measure in a visual way the speed in terms of how much the plane moves in 0.1 second compared to the length of the fuselage. And comparison was pretty good. It was within my desired 10%.
That'd be fun for us just to have regular launching without the telemetry, to watch the parachute
Yep.
in a single frame. That'd be very cool.
Yeah, this is interesting. And it's not hard to do. If you have I used a very simple video camera, just need to mount it on a tripod, because it has to be far enough from you to make parallax and distortion negligible. We tried to do that with you, I think, Bob.
Yeah, we never got to
Yeah.
the analyzing part, I don't
Yeah,
think.
right. You have the videos somewhere.
Okay, well,
Very
thank
good.
you.
Yes.
It was great.
Thank you.
And that concludes the evening's festivities.
Tim.